Good afternoon, everyone. I'm Shiyu Sui from Southeast University. Today, I'm going to talk about chloride binding assessment in C3s systems with calcium clay. There are 4 parts in this presentation. The first one is background. The second one is materials and method. The third one is results and discussion. And the last one is conclusions. Now, let's have the first one, background. CO2 is very common in our daily life. When there are more and more CO2 in the air, the greenhouse effect will be caused, which can lead to the global warming. Since the environment is very sensitive, 1 degree temperature increase can lead to serious ecological problem. Therefore, global warming slowly becomes a serious problem. In our building materials field, actions should be taken to decrease CO2 emission. Cement is one of the most widely used materials in the world. The house, bridges, and tunnels are all made up of cement, concrete, and steel. From the pictures in the middle, we can see the CO2 release from concrete and steel is around 22%. Therefore, new building materials are needed for low carbon emission requirement. To decrease the CO2 emission, a common method is using supplementary cementitious materials to replace part of the cement clinker. Usually, we use slag, flash, silica film, and so on. Most of them are byproducts from industry. However, the storage and production cannot meet the increasing demand of cementitious materials. New types of supplementary cementitious materials are needed. Nowadays, LC3, which is made up of cement, limestone, and calcium clay, is a very promising cementitious material because both calcite and clay are abundant in the world. To evaluate a new cementitious material's durability is a very important factor. As far as we know, steel chlorine is the major reason to decrease durability. Therefore, chloride ions should be paid much more attention, because chloride ions are quite common in some environments, such as the bridge. Chloride from the sea will slowly penetrate inside the structure. When there are more and more chloride around the steel, corrosion will happen. From the picture below, it is clear that too much chlorine product will lead to the structure destruction. Therefore, chloride resistance of LC3 cement needs to be assessed. Materials and method. In this study, we used pure C3s, a low-grade calcium clay, and a commercial limestone. The metallurgical content in calcium clay is around 50%, and we can find aluminum is from the calcium clay. 4 different mixtures are used in this research. The picture on the right will only show 3 mixtures. 100% C3s, C3s with 30% calcium clay, C3s with 30% calcium clay and 15% limestone. And for pure C3s, there are 2 different water-cement ratio. One is 0.5 and the other is 1.0. For the method, except for the normal method we show here, such as XRD and nitrogen absorption, another method is also used to calculate the phase assemblage, mass balance. Here we show the calculation process. At the beginning, C3s and the calcite amount are from XRD analysis. Then we know the reacted oxide amount. And for the CH, AFT, and AFM, the contents are also from XRD analysis. At last, the remaining calcium oxide is going to form CaSH. Finally, we can acquire the phase content in different systems. For the chloride binding capacity, we use the equilibrium method, which means few grams of particles are put in different concentrations of sodium chloride solutions. After 2 to 3 months, the bound chloride and free chloride relationship are investigated. Results and discussion. At the beginning, some basic experiment was done on C3s system. It can be seen that when the hydration time is longer, such as this 28th day, there will be more calcium hydroxide and less C3s. And for the pore size distribution, pore volume and surface area are shown on the right and below. With the increase of hydration time, the amount of small pore between 2 to 5 nanometer increased a lot. Since most of the surface area is from CASH, therefore 2 to 5 nanometer pore is representative for CASH. And also we can find that with the increase of hydration time, more and more CASH are formed. The binding capacity is tested by using the equilibrium method. Here is our result. It is clear that with the increase of free chloride content, there will be more bound chloride. And we can also see the lines are different. In the figure, we can see the pure C3s shows the lowest binding capacity, and the systems with only clay show the highest binding capacity. Then, by using the Friedrich isotherm to fit the curves, we can get the parameters as shown in the table. The fitting for the systems with clay is quite good. However, for the pure C3s system, the values are far from 1, but we can still use the parameters values to compare the binding capacity. Then combine the figures and the table together, it can be concluded that the higher the alpha, the higher the binding capacity, and also the lower the beta, the higher the binding capacity. The binding capacity difference is from the phase difference. Here, we do some research on the hydration product. As shown in the figure, the hydration products are quite different in different systems, especially for AFM phase. For C3s 0.5 and C3s 1.0 systems, the main hydration products are CASH and calcium hydroxide. However, for C3s plus clay plus limestone system, hemicarboaluminate and monocarboaluminate were formed, thanks to the limestone reaction with aluminum phase. These two phases is beneficial for the chemical bond chloride formation. Maybe this is the reason for the high binding capacity of systems with clay. Then, to get the quantitative results, we calculate the phase content in different systems by using mass balance method. It can be seen that higher water-to-symmetry ratio leads to higher degree of hydration in pure C3s systems. For systems with calcium clay, AFT and AFM were formed because of the aluminum and impurity of clay. The analysis of the phase content is helpful for the binding capacity, because for the pure C3s systems we can see the CASH content is different for 0.5 and 1.0 water-to-symmetry ratio. However, the binding capacity we showed before are quite similar. Therefore, the CASH content is not the only factor which can affect the binding capacity. And also, for the systems with only clay, we can see there is no AFM, which means MC and HC formed. However, there are a lot of aluminum in the pore solution, so when the chloride penetrates inside the pore solution, the Friedel salt can also be formed, and which means the chemical bond chloride will be formed. Then we also do some analysis on the pore volume change. This result is from the natural absorption. It is clear that when clay is added to the system, the pore size becomes larger. When we quantify the pore volume, it can be seen that C3s system shows the lowest pore volume, and C3s plus clay plus limestone presents the highest pore volume. So, another very important factor is the surface area. For the surface area, it is clear that all the peaks are around 2 to 5 nanometer. However, we can also see the pure C3s system shows the highest peak, and the systems with only clay show the lowest peak. And this is from the CSH. In pure C3s systems, there is more CASH, so there will be more surface area. And also, when we quantify the surface area, we can also see the C3s plus clay shows the lowest surface area, while pure C3s demonstrates the highest surface area. Usually, surface area is related to the physical bond chloride. However, in our research, there is no clear relation between surface area and the physical bond chloride. In the figure on the left, the physical bond chloride is from the total bond chloride subtract the chemical bond chloride. So here we see no clear relation. And also, for the figure on the right, we can see pH shows an influence on the binding capacity. When pH is increased from 7 to 10, the binding capacity also increases. However, when we increase the pH from 10 to 30 and 40, the binding capacity decreases a lot. The table also shows that the pH of the host solution is different. Therefore, the factors affecting binding capacity is complex, and more research is needed for the mechanism of chloride binding. So in our research, the following conclusion can be drawn. The presence of calcium clay can improve the chloride binding capacity, which comes from the improved chemical binding capacity. The water-cement ratio shows little effect on chloride binding. And also, there is no clear relation between the surface area and the physical bond chloride. The last one, surface area, calcium to silicon ratio, pH of the final sodium chloride solution, and the CaSH content could affect the physical binding of chloride. Thank you for your attention.